Hello everyone and welcome to another solutions video. Yes, I am back and today we are going to be discussing solutions for educational round 120. I've done first four problems, so I'm going to explain their solutions. So problem A, in this problem we have three sticks length L1, L2 and L3. Now we want to take any of the one sticks. Let's say I take L2. I break it down into two other sticks of length L21 and L22. Now what I want to do is I want to utilize all these four sticks 1 2 3 4 to make a rectangle. Now what a rectangle is, obviously the opposite sides are equal. So what I want here is that among these four sticks, two has to be equal and then the other two has to be equal. So let's say L1 and L3 were not equal, so they cannot be the opposite sides, they will have to be the adjacent one. This is L1, this is L2. Now what I will do is I will have to break this is L3. Now what I will do is, let's say L1 and L3 were not equal, so they are adjacent. Now what I will do is I will break L2 in such a way that some part of it is L1 and other part of it is equals to L3, and then I'll be able to put the first part L21 here and L22 here. However, if L1 and L3 were equal, then I have this option, but I have another option. And what is that option? Let's remove this. The other option is I make L1 and L3 opposite, but this is only when L1 and L3 are equal. And in that case, I will just break L2 such that the two parts are of equal length. Now for this, I will need L2 to be divisible by 0. Sorry, divisible by 2. So these are the two possible things. We can try for every stick. We can try breaking every stick, and if for any stick we are able to do, we will print yes, otherwise no. And here's the implementation. So I first of all take an input in a multiset. This is, I think, overcomplicated implementation, but this is what I did. So first of all, I take the input. I take in the three lengths. I'm using multiset because lengths can be equal. Then I put them in a vector and then I iterate the vector, and X is my current stick that I will be breaking. So first of all, I remove that from the multiset. I get the other two sticks, so A and B. And now if their sum is equals to X, that is L1 and L1 plus L3 equals to L2, right? Then I can break L2 into two parts such that one is L1 and other is L3. So then I can say yes. Otherwise, if they are equal and it is divisible by 2, which was this case, then also I print yes. Otherwise, if I cannot do it for all the sticks, for any of the sticks, sorry, then I just say no. Okay, problem 2 or problem B, Berland music. So in this problem, we are given scores of some music, some songs. So we are given scores of some songs. It is an array P, and P is a permutation of 1 to 5. So any rearrangement of 1 to 5. So what we have to do? So what happens first of all is a person either upvotes them or he either downvotes them. And after upvoting and downvoting, what we want to do is we want to reassign a new score, Q1, Q2, Q3, Q4 and Q5. And the property this score has to show is that whatever song which was liked, right? So let's say P1, its new score must be greater than any song that was disliked. So P3 and P5, okay, so the song 3 and song 5, their score, so let's say the scores, so the scores of song 3 and song 5 must be less than the scores of song 1 and song 2 and song 4. So what I want is 3 and 5, since they were disliked, they have to get lower score than all the songs that were liked. Okay, and the scores are from 1 to 5 only, right? So this is the scoring space. So as you can see, also before that, the way we adjust the score, right? The way we adjust the score, so P1 to Q1, P2 to Q2, the cost of adjusting the score is absolute P1 minus Q1 for all, so for Pi minus Qi, and we want to minimize this score. So we want to tell the new permutation Q that minimizes this score. So here, as you can see, that S3 and S5, they must get the score 1, 2, and S1, S2, S4 must get the score 3, 4, and 5, right? Because 1, 2, both of them will be smaller than all of these 3, 4, 5. So this much was pretty simple. Now how do you assign which one which? So as you can see, the song 3 and okay, sorry, so let's say the song 3, which had score P3, right, was, so P3, let's say, was 2 earlier. No, let's say it was 3, and P5 was, let's say, 4. So here you can see that there are two options. Either you can assign P3 1 and P5 2, or P3 2 and P5 4. Sorry, P5 1. So either you can go like this, right? This goes here and this goes here, or you can just go like this. This goes here, this goes here. Now, which is optimal? So the optimal one is obviously, which you might be thinking without any proof, is that you make the smaller one the smaller and the bigger one the bigger. And this is indeed correct. This is the optimal rearrangement. And the proof kind of for this is, let's say I have these 4 values, right? So which are the songs. So let's take it for let's say S1, S2, S3, S4. These are some values. And let's say I want to change all these values to these values, new N1, N2, N3, and N4. Now, and if changing anything is costly just like this, right? So the cost of changing anything is the absolute distance. So you will see that the optimal approach for this is you move the lowest one to the lowest one, the second lowest one to the second lowest one, the third lowest one to the third lowest one, and the fourth lowest one to the fourth lowest one. And as you can see, there is some overlap, but this is unavoidable. In any approach, if you were to try to move S1 to N2 and S2 to N1, you will see that there is some extra cost, especially this is being repeated twice. So this is the optimal one. So as you can see, we just want to reassign these values such that they are assigned in an increasing order. So P3 and P5, and let's say S1 was 5, this was 2, sorry, this was 1 and this was 2. So how will you assign here? Here you will assign like this. So 1 goes to 3, the smallest goes to the smallest, 2 goes to 4, and 5 goes to 5. This will be the optimal rearrangement, and in this case the cost would be minimum. So the final permutation you will get, Q would be like this. So S1 was 5, it remained 5. S2 was converted to 3. S3 was converted to 1. S4 was converted to 4. And S5 was converted to 2. It remained a permutation, and as you can see, the downvoted songs are given the lowest values and the upvoted ones are given the higher values, 5, 3, and 4. So I think it wasn't that difficult of a problem, but this result you might not have known but might have just applied. So this is the result. You can learn it now in case you didn't know that it actually works in every case. And the implementation somewhat again overcomplicated, but I'll explain. So what I'm doing here is, first of all, take the input A, and now I'm keeping an inverse mapping. So basically at what index some value is. So this is the index for any value. So this map would give me the index for any value. Now I take in the input string, and then I'm storing two sets. One is the liked one and other is disliked. So anything that is disliked goes into the disliked set. Anything that is liked goes into the liked set. And then, so now I know, so if there are x things that were disliked, right, which is dl.size, then I know that the values that are going to be assigned to those songs will be from 1 to x. So I iterate from 1 to x. I get the song which was assigned, which was given dislike. So among them I get the one which had the lowest value because I'm iterating from lowest. And then I get its index and I reassign it. So whatever the lowest value was for disliked set, I get it. So that is iterator. I get its index and assign it I, because I'm reassigning those values from 1 to x. And similarly I do for the liked set from x plus 1 to n. I get the like set, I replace it, and then I erase it. So yeah, this was the implementation. Now let's move on to the third problem. A good amount of people did second problem as well. That is great. So the third problem, set or decrease. So this was a nice problem. In this problem we have an array A, just like always, we always have an array. So let's say we have an array, and now what we want to do is we want this sum, the sum of its elements, to be less than equals to k. So sigma ai needs to be less than equals to k. Now to make this happen, we can do operations, and what an operation is, either choose an element and decrement it, or choose two elements ai aj and assign aj to be equals to ai. So how can you do it? Well, as you can see, this reassignment operation, so whenever you are doing it for two unequal values, right, it is never less optimal than decrementing it, right? Because let's say we had 3 and 5. Since these are unequal, I can choose this to be j, this to be I, and I can reassign it, and this way my sum will reduce by 2, right? However, if I were to perform the operation 1 on j, my sum will only reduce by 1. So this is almost always preferable, right? So what I can do is I can get the sorted version. So let us assume A is sorted now. So A1 would be the smallest one. Now what I can do is, in one operation I will assign A6 to A1, then in another I will assign A5 to A1, and so on up to A2 to A1. And if at any point my sum becomes less than equals to k, I can just say that yeah, I have gotten the required constraint, and now I can print the cost incurred. However, what if it is something like this: 4, 5, 6, 7. If the array is like this and the sum that needs to be less than, so k is, let's say, 10 in this case, or let's say 12 in this case, even if every element were to become 4, in this case, even if every element were to become 4, we will still have the sum more than k. So in this case, we will have to make everything 3. So for that, we can first of all decrement the first element and then do the same thing, and this will be pretty fast, pretty low cost. So for now we have a pretty good strategy, and this is based on basic observations that first of all a1 needs to be at least this total k by n, right? Because in the in the previous example, if even if everything was 4, its sum won't be less than equals to 12. So I need it to be at least 3, at maximum 3, because 3 times 4 is 12. So a1 needs to be like this, and once a1 is this at least this much, then I can just reduce all the elements using the second type of operation. First of all, reduce a6 to a1, then a5 to a1, then a4 to a1, and so on. However, there is a problem, and the problem is, what if, so like take this example. So here, what is the sum? Okay, let's take it 20, 20, 30, 32, 34, 35, 36. Let's say I wanted it to be 12, the sum to be 12. Or I can just take a sample. Why am I stressing my brain? So let's take this example. 1, 1, 2, 2, 3. So 1, 1, 2, 2, 3. 3, and then 6, 6, 8, 10. 2, 4, 6, 8, no. 1, 1, okay, there are 3 ones. So, and we want it to be less than 1. Okay, we want it to be less than equals to 1. So, if I want it to be less than equals to 1, k is 1 and n is 10. So, this goes to 0. So, if I try my previous approach, I first of all make this 0, and then I apply 9 more operations, or actually 8, just 8 more, and the array becomes like this, and the sum is less than equals to 1. But this is not optimal. Reason being, in the samples we have another approach. What we can do is, if we reduce it to -2, then we just need to reduce these 3 to -2. So total operations are 3 plus 3. We just need to reduce this much to -2. So total operations are 3 plus 4, 7. So as you can see that we want a1 to be at least to be at maximum k by n, but by reducing a1, we can get probably a better solution with lower cost. And if you were to brute force a little bit, you will notice that let's plot a1. So this is what I brute forced. Let's say this value was k by n, and this is like negative infinity. So if you were to plot it, right, then the cost would be something like this. Okay, I'm not sure this is the correct curve, but it would be something like this. First of all, it would probably reduce and then increase again. However, we cannot apply ternary search on it because it can be like this. So as you can see at 2 values, let me just plot it here. So it can be like this, and we cannot apply ternary search when the value is same at 2 different positions that are not the peak. So ternary search can also not work. So what can we do here? Well, now so the reason I explained this ternary search thing was just because I thought this was interesting. Now let's go to the actual solution. So now we know that ternary search doesn't work. So how can we do it? Well, let's see. Now imagine how you will do the ternary search. If ternary search were to work, what you would do is you will fix some a1 value to which you will reduce a1 to, and then perform the operations a7 to a1, a6 to a1, a5 to a1 and so on up until the sum is greater than k. However, if you can see that some portion on the right side is converted, so I'm going to call them converted to a1. A1 is reduced to some value on which you are ternary searching, so let's say some x, right? This remains same. So if you want the sum to be less than equals to k and you know this value, so let's call this value p. Okay, so this sum is p, then really you have this much space, right? So the sum of a1, a5, a6, a7 has to be k minus p. And if it has to be k minus p and we are eventually converting everything to be equal, then everything has to be k minus p by 4, which is the number of elements. So let's say k was 100 and p was 50. So 50 by 4, what is 50 by 4? I think around 12, right? So that means that a1 will be reduced to 12 and then we will reduce all a7, a6, a5 to 12. So as you can see, not just what value we are reducing to matters, but we can also get something similar by fixing how many we are converting, right? Because here you noticed, if I fixed how many I am converting, again I'll be able to reach x, and that would be 12. So that's how I approached this solution, that I was trying ternary search, that what I would do in ternary search, and I saw that in ternary search I'm fixing 12, and from that I'm getting the length of the suffix that I'm fixing, which was 3 in this case. So what if I fix the suffix? If I fix the suffix 3, then I will be able to get 12, that is x. So we just have to fix the suffix. So if we fix the suffix, we'll be able to calculate what value we want a1 to become, and then we will calculate what was the cost, and for all the suffix we can calculate this cost and then take the minimum. So let's have a look at the submission. So here is the solution. So I take the input, I sort the array, I calculate the prefix sum, and now notice I'm not calculating the prefix sum from 0, and the reason is I want this p value, right? And this p always starts from the first index, which is a2. So that is why I'm just calculating that. Then here I go from n minus 1 to 0, and what this means is, if I is n minus 1, that means, so if I was 4, right, then I depict this situation that I am leaving from index 1 to index 4, sorry, so I is 3, from index 1 to index 3 as it was, and I'm converting the remaining suffix and a1 obviously. So I get the sum by using prefix, and the number of elements that I'm changing is n minus I, and required value is k minus sum, right, k minus p, and then I divide it by count. Now this value, if it were to be negative, right, if k were to be negative, so let's say it was minus 12 and n was, let's say, 5, then the division would give me minus 2. However, I would want it to be minus 3. So this is the reason I was thinking that maybe I'm missing some, plus minus 1. So I took the chance, and what I did is I'm iterating from the required minus 5 to plus 5 and calculating the cost for that value for reducing a1 or a0 to x. Now this wasn't really necessary, but this is a nice trick you can do whenever you are thinking that you have a plus minus 1 issue. So first of all, I check that the sum plus count times x. So this is the total sum. If it is greater than k, then of course this is invalid configuration, and then I calculate the current result. So first of all, I reduce a0 to x, and then I perform count minus 1 operations to make the other remaining suffix elements to be equals to a0, and then I just assign answer to be minimum of answer and the current answer. And this was the solution. I'm not sure how well I explained it. I sucked at it myself, so leave me alone. Okay, problem D. This was the only good problem, I think, because I was able to solve it. So in this problem, we are given a binary string. So like 1 1 0 0 1 1 0. And what we want to do is we want to pick any substring in which the number of ones is equals to k, and then we can reshuffle it. Okay, so let's say k was 2, so I pick this substring and then I can reshuffle it. So when it got reshuffled, I will show the reshuffled one like this. So let's say it got reshuffled like this, right? So I can do this operation only once. Okay, however, what I want to do is I want to count that after doing this operation once, what are the distinct strings I can get. So as you can see, after performing this operation once, I was able to get this, but I can also get something like this and many others. There's also, what if I were to choose this much? In that case, I'll be able to get 1 1 0 1 1 0. Wait, 1 1 0 1 0 1 0, something like this, and some other permutation, and so on. So there are a lot of unique strings that I can obtain by just one operation, and that is what I have to count. So let's see. And here notice that we are making a substring only when the count of ones is k. So the zeros kind of don't matter. We just have to worry about where ones are. So let's see. So let's say this string is like this, right? There are 4 ones. There are some zeros in between, right? So there are some zeros in between. Let's say there are, so whatever. There are zeros in between. So, okay. Now, if k is equals to 2, then I can pick a substring that has only exactly two ones. So take this, I can maybe pick this, maybe I can pick this, maybe I can pick this, right? So if you look at it carefully, you can see that when I am taking these two, right, when I'm taking exactly these two, I am never taking the other ones. Now this was obvious, I don't know why I stressed that, but when you take these two, you are not gonna be taking anything from here onwards, right? So the string that you are gonna be shuffling is this much. And how many different strings you can get after shuffling this? Well, let's say its length is len, then you will get len ck, right? You apply the combination formula on k once, or this is also equals to len c len minus k. You either select positions for zeros or select position for 1, and you will get the unique substrings. But if only you were to consider this much. Okay, now let's look at the rightmost part. So in the rightmost part, if you were to take the rightmost two ones, so you will be able to work with this much substring. And here again, the formula for rearrangements would be this much, len c len minus k. So this was some length. But now let me just erase that because kind of irrelevant. But now you also have this thing in the middle. So if you were to take these two ones, then here again, whatever the length is, the same formula applies, right? But as you can notice, there is some overcounting going on. So what is the overcounting? So first of all, let's assume there was no overcounting. Then what is the solution? Well, then the solution is very trivial. What we do is we take the maximum substring for every length k. So like first of all, I took this much, then I'll be able to take this much, and then I'll be able to take this much. And whatever their length is, so let's say L1, L2 and L3, I say L1 ck plus L2 ck plus L3 ck. This is assuming there is no overcounting, but there is definitely overcounting, right? Let me show you one example. So if you were to select these two ones, right, in this range and do a permutation, one string you get is 1010110. And if you were to select this much, right, and do another permutation, another rearrangement, what you can get this again, 0110. So there is overcounting. Now we want to eliminate that, obviously. So let's see how we can eliminate that. To see what the overcounting is, let's get that again. 1 2 3 4. So there was a 1 here, 1 here, 1 here, and 1 here, and k was equals to 2, right? So for the first window you took, it was like this, and the second window you took, it was this much, right? Now when can there be overcounting? There can only be overcounting when, first of all, when you are rearranging this window, right? When you are rearranging this window, then if you keep this at where it was and just move this one somewhere, so let's say you get something like 1, a new 1, and since the other ones will remain at their position because we are doing this operation only once, you'll get this string. And if you were to do operation on the second window, then you can get this only if this remains at its position, and then you can move this one to here, right? So notice that the difference in every window is of 1 1, right? It is very confusing, 1 1. So the difference between these first two windows was the first one didn't have this, the second one didn't have this. Sorry, the first one didn't have this one, and the second one didn't have this one. So to get equal string, after the operation, we're gonna want this one that they don't have to remain at the same position. So that is why I wanted this one to remain and this one to remain at the position, and then wherever this one goes, right? This one can go here or here or here, wherever. These configurations will be captured by the first counting and the second counting both. So this is what we are overcounting. Now if k was equals to, let's say, 3, it remains same, right? Let me erase this. Erase. So if it was like 3, 1 2 3 4 5 6, and there are some zeros in between, then you're gonna want to fix this, and then do the rearranging in them. And as you can see, this rearrangement will be captured by this window as well as by this window. So that is also like a similar problem of counting what we previously counted. In this case, just the string is removed from this part and this part, and the k is equals to k minus 1. So let's do this. Here, first of all, I have written some code for what we say NCR. So for calculating NCR in speed. And then what I have, first of all, I take the input, right? And I'm first of all doing some edge case check. If k is 0, return 1. If the count is less than k, so if we cannot do operation, again return 1. Otherwise, first of all, I'm going to do it for the original string. So what I'm counting, right? What I'm counting is the thing I described in the beginning. What I'm counting is just this L1CK plus L2CK plus whatever you get. Okay. So we have, first of all, we get the size. So this is the function that will do it. Get the size. If n is not, if n is 0, then return out. Now I have this count. This will keep track of how many ones I have encountered, and this is the answer. X, forget it. Then I have I and j. So I will move forward, and so I would be the forward pointer and j would be the backward pointer. So whenever I do not encounter 1, I continue. So whenever there is a 0, I don't care. Otherwise, I increase the count, and every time count becomes greater than k, right? Then that means, so if it was like this, then, and if j is here, which is 0, if whenever I reaches here for k2, right, the count became 3, so that means the window is this much. So what I do is, forget this again. I do this calculation. I minus j is the length and k is fixed. So NCR, and then I take modulo, and then I move j forward while count is greater than k. So because it can be like this, right? And j might be here. So I'm gonna keep moving it, and I will move it up to here. So, and then I will continue again, and I will go forward. And because of the way it is written, I'm gonna, after the loop, check this again. Forget this again. If count is k, do the same operation and then return answer. So now I have the original, this value which has overcounting in it. And to remove overcounting, first of all, I remove the string, like this part from back up to the first one that is encountered. So that's what I'm doing. While s.size, whenever I encounter a 1, I'm gonna break out after removing it. Otherwise, I'm just removing it. And then I do the same thing, but from the front. That is why first of all I reverse and reverse back again. And here's the double count. I remove double count from answer, take the modulo, check for negative, and print the answer. So yeah, that was the solution for problem D. Hope you found it useful. I doubt it. I'm not sure how well I explained, but hopefully it was good. And I'll see you guys next time. Make sure to subscribe. What is my rank? Okay, a positive delta. Good enough.